Good afternoon, everybody. Welcome to this talk about squeezing Unicode names into Ruby regular expressions. My name is Martin Dürst. Say Martin と呼んでください. Okay, before we start, actually, yesterday I did a little search and I found this snippet that said that RubyKaigi 2024, Martin Dürst and so on, discussed the future of Ruby expression. Yeah? If you looked at it discussed, well, that would mean that AI saved me a lot of work. もうやったので、もう書いていいですよね。So, well, maybe AI has a lot of foresight that already thought about this evening, or whatever. Well, it's one of these hallucinations, or it probably just saw old RubyKaigi data, and from there it inferred that if you give a Ruby talk, then you have to say discussed, because that applies to most past RubyKaigis. Anyway, so this is information about me. I want to especially mention here that this work was done with Kohei Eda, a student of mine. Unfortunately, he isn't here. He likes trains very much, and so he took a job in a train company. And well, in Okinawa, there are not too many trains anyway. So, okay, so these are the contributions to Ruby. I hope Unicode 15.1 comes before Unicode 16 comes. So we are talking today about regular expressions and Unicode properties. And the general way you use that, you have a string and you match it with a regular expression. And in the regular expression, you can use this \p, and then you can use a property, or actually in this hiragana case, it's actually a property value. It's the property value of the string property. And this matches a hiragana character, and because we have a hiragana character here, it says it matches a position 1. Okay. But what we would like to do, or what I would like to do, you should tell me after the talk whether you would like to do that or whether you don't care. So we would like to say we want to match a character with the name hiragana letter ni, and then it should match this hiragana letter ni here, but what we get currently is invalid character property name, and actually it thinks that this is the property name. Yeah, its only name is would be the property name, and this would be the property value. Okay, and well, actually, why would we need that? That's a good question. Because we can already match like this directly on the character, or we can match with Unicode code point escape. So it's interesting in some cases, but not really necessary. Okay, so this is data from a few years back, but the situation is essentially the same. Unicode has very good support for binary properties, because the way it handles properties in the regular expression engine is very well done is very well suited for binary properties, but it doesn't have much support for multi-valued properties. Only at that time it was 7 out of 43. It's probably now still 7 out of a bit more, because Unicode likes to add properties. And the name property is one of the non-supported multi-valued properties. So here are examples. You see there are all kinds of names, names like hiragana, Latin capital letter A or hiragana letter A, which are descriptive. Semi-descriptive names like this, you just have the actual code point number in the name. You still know it's a unified ideograph, a kanji. You have very short names, even for very special characters like emoji. But you can also have very, very long names, and if you read that name very carefully, you can actually figure out that what does it? Upper center to middle left, and middle right to lower center, so it's two diagonal lines like this in a square. So this is, and it's light, yeah, thin lines. Anyway, and you can find more details about the name properties in name property in section 4.8 of the Unicode standard. Okay. What this isn't written down anywhere in the Unicode standard or so, but what I actually, when I worked on this, figured out is that the name property is the oldest character property. Yeah, it exists since before Unicode. It was widely used to define, definitely identify characters across encodings. Yeah, when we had ISO 646 in Europe, where instead of curly braces and so, the Germans had his umlauts and the French had the accents and so on. Or then later in ISO 8859, the name was used to say this is this character. Yeah? Nowadays, Unicode ISO 10646 is the center to just identify a character. You know that Unicode and ISO 10646 were developed and are developed in parallel. Unicode has a lot of properties. ISO didn't really have properties. Now they have a few, but they always had the name. Yeah? They always had the name, and they insisted on names even more than Unicode. The names are also translated into French, maybe even into Russian, because ISO standards are often translated into French and Russian. These are the three official languages. And also into national standards, for example, GIS X0221. So the question would then there be also, do we also want to support the Japanese character names? Yeah, that would be that's not done here in the talk. What's also very important is that Unicode character names never change, never change, never change. If there's an error, it's never changed. There's an alias, a fix, but the name is never changed. It's never, even in Unicode code points. Unicode has, I think it were version 5, they moved around over 3,000 Korean code points, but they never changed names. Yeah? So it's also in the first file with Unicode data, the file Unicode data.txt. The code point comes first, and immediately after that, it's the name. Yeah? So you see that this is actually a very important property. Okay. But on the other hand, it's also this is a strange kind of English. Don't think this is correct in English. It's the most multi-valued property. Yeah, it has the most values. Each character has a different value. Most other multi-valued property like age, like skip, like block, and so on, it's always lots of characters have the same, and then some others have others, and so on. Okay, so it means that we need a lot of data, and that's the main part of this talk. So what we need a function that we can give it a name, and we get back a call point. Yeah. The reverse is also interesting. There's some other interesting stuff, but that's not what I'm currently discussing about. That's maybe future work. Okay. So how could we do that? If you want to do it just in Ruby, you use a hash. Yeah. We could also have an array with binary search, or we could use a search tree. And well, what do we expect? For hashing, it will use lots of memory. For binary search, it will lose lots of memory. Can we make a search tree more compact? Let's see. Okay, we will use a search tree. The search tree that we will use is called a trie. The way it works is we start with the empty string at the root, and then on each level we have one child for each character that we can choose. And then the next character is on the next level, and so on. So to get to hiragana, which is just the start of the name, we choose from the start, we imagine you have 26 or actually 36 different streets going out from a crossing. You look street H, you go down that street for a block, and then you get to the next crossing, and then you choose the I street, get down a block, choose the R street, and so, and on you go step by step for each character. And so each crossing or each node in this tree would then look like this. We have at a certain crossing, well, we are now at the crossing that stands for Latin capital letter A. We already passed quite a few crossings. And here we can actually have a call point. We can be done here because Latin capital letter A is a character name. Yeah? But we can also, it could also be that the name is still longer. For example, there's a character called Latin capital letter A. So we need to go a next step. So if we are done here and look for the call point, we take the call point here. If we want to go down the A street, we have a pointer here to another node. And we have, overall, we have 37 entries here. Yeah? So it's quite a bit. And so what size do we need here? Well, the call point is 21 bits. Here's the calculation. The pointer, well, in general, pointer would be, these days, would be 64 bits. But we can use relative pointers. So it's only 32 bits or less. And so to make things easy, we choose 32 bits, which is, depending on the machine, it's long or whatever, it's just U32, uint32 to be exact, yeah? And so we are working with an entry size of 4 bytes. And here are these 4 bytes, or 32 bits, numbered from 0 to 31. And for a call point, we would just put the data in the lowest 21 bits. And this is actually how it shows up in the data file in our implementation. Lots of comment for debugging, but this is just the data. And for pointer entities, we don't know exactly how many bits we need. Actually, it turned out that during the implementation, we started with quite a few nodes. And so we need a lot of pointers, longer pointers. And then we were able to shrink that. And with the space that we freed, we were able to implement some more stuff and then shrink it again. Yeah. Okay. So if we just do that very simply, we get to an overall node size of 148 bytes. And it depends on how we calculate, but we need on the order of 100,000 nodes. So we would, at this stage, need on the order of 50 megabytes. And we are not doing a very good job so far. Yeah, but now we come to the squeeze, yeah? Okay, so when you learn about trees, if you ever did that somewhere in computer science or in a computer science data structure class or whatever, one of the very important things that you have to learn is in trees, most nodes are leaves. For binary trees, it's half. Half of the nodes are leaves, yeah? But if we have 4 children per node, actually 3/4 of the nodes are leaves. And in our case, we have 36 children per node, so it's kind of like almost every node is a leaf, yeah? And so if we can somehow reduce leaves, we save a lot of space, yeah? How do these leaf nodes look in our case? We have one code point, and then we have 36 nil pointers, yeah? We don't have any additional data. So then what we do is we say, okay, if flag 29 is set, instead of having a pointer, we have the code point directly here, yeah? We know for which letter that is, so it's directly here. And, okay. So, with that we save quite a bit. Next thing is, we still have nodes where we have some pointers to other nodes, but of these 36 different roads that go off that crossing, maybe only 2 or 3 or maybe only 1 is actually going somewhere. So we can compact these nodes. One way is to use an additional index. We have an additional little index that says, okay, for letter so-and-so, it's at entry so-and-so, then we can compress the entries. Or we can do linear search with labeled entries. And that's what we do. So we have these labeled entries. And we use the bits here, 6 bits, because the name characters can only have 36 different values, only uppercase letters or numbers. There's also hyphen and there's space, but they are not used when comparing names. So we use these. We have reduced the pointers here to 21 bits, and the code point is also 21 bits, so we can use these 6 bits here to say which direction it is, and we can distinguish these two with this code point bit here. And then we have a list of labeled nodes, and to distinguish them from full nodes, we use a labeled first, I'm sorry that this doesn't show up, a labeled first bit and a labeled last bit, so that we can know from where to where this goes. Okay, so that compresses the nodes where we have some branch off, but not so many. Now actually, if you look at these character names, sometimes you have, like, if you're at Latin letter, a Latin uppercase letter, no, Latin capital letter, then you have A, B, C, D, D, you have all the alphabet, yeah? But in other cases, you all have just one. At every crossing you come, you have just exactly one street to go, yeah? Like here, we have this name series, face with symbols covering mouth, yeah? And apparently there's lots of smiling faces in Unicode, yeah? But only, and actually some crying faces also, but only one serious face. Unicode doesn't seem to be very serious. So the closest to this name here is this service mark name. So up to here we go together, and then we have a branch for I and a branch for V, yeah? And then we just go down one street after another, and it's just a linear down the tree, yeah? And we would only need 4 bytes per character, but 4 bytes is still a lot, yeah? Actually, 6 bits should be enough, yeah? So we should be able to squeeze 5 characters into one entry, into one word. So how do we do that? Well, we create these radix branches. There's radix trees that work like this. Radix branches use between 2 and 8 of the entries, 4-byte words, yeah? The first entry is labeled with a radix flag to show that we are on a radix branch. And then we have 3 skip bits that show how many entries are in this radix branch, and this is used in the labeled mode to skip over the radix entry. And then we have 0 to 6 intermediate entries that contain 5 characters each, and the last entry with 1 additional character if necessary, and the payload, yeah, for the next step. That might be a code point where if you're at the end, or going on. And with this, the first radix entry looks like this. We have the radix flag here, and this is a bit irregular. The skip bits are here, and then here we have the first character, and then the second, the other ones go here. It's interesting, these are little endian. It turns out that was easier the code works out nicer. Yeah. I always thought big endian was natural, but now I understand why little endian was implemented by Intel, maybe. The intermediate entries, they just have lots of characters, 5 characters, yeah? And then the last entry has maybe a code point bit, and potentially the last character, and then the payload, yeah? And, sorry, here, this doesn't show, but this is kind of the way, let me see, yeah, you can make this. So this is the way the data looks this is kind of shifted by 6 bits and so on. And the first one, it says skip 4, and then 1, 2, 3, 4. And here's the last one, which is a co-point. And this is for a prefix of south, well, whatever, south and southwest start arrow. Okay. Okay, so with these radix branches, we can actually squeeze. We actually need 0.9, in the best case, 0.99 characters, bytes per character. Okay, then one other big saving is that a lot of names are defined algorithmically. Some are defined by Unicode, 11,000 Hangul syllables, and then all the kanji and some Khitan and Nushu characters and Tangut ideographs. And then there are also others that are not defined by Unicode, but that my student actually looked at the data and found out, well, these are just decimal numbers, for example, that go from 1 to, I'm not sure how many hundreds. Variant select is the same. Braille dot patterns just use the dot numbers 1 to 8. So they're also, it's easy to convert them to a co-point algorithmically. And what we do is we use a special co-point for each range, and then that creates a much smaller, we don't need a lot of subtree there. Okay, a current usage. Actually, I didn't manage to put this into regular expressions, but I added a method to Unicode name to co-point to the string class. And so you can actually use it that way. I mean, this is a very short name here. And testing, all of Unicode data and all the Hangul syllables and some special cases all pass the tests. And that turns out to be about 300,000 names per second in testing. Okay, the current memory needs are about 400,000 bytes. It's definitely less than the raw data, which is about 1,100,000. It's more than the gzip data. There's actually research on how to use some gzip-like encodings and then still be able to jump in somewhere. But that's very complicated stuff that I didn't want to go to. Further improvements, we still have some bits, maybe a bit we can free up. If we have some additional ideas how to use these bits, then we can squeeze things more. We can look at more functionality, for example, character sequences, and so on. So in summary, we implemented co-point lookup from Unicode character names. We used tries, radix trees, and careful bit squeezing to save memory. And the implementation passes, but still needs a lot of cleanup. It's now available on GitHub, but please don't look at it too carefully. Okay, and we really would like feedback. Well, whether you want that, where, how you want to use it, and so on. And it would also be interesting to know how much memory you're willing to spend. It's all I mean, the code, not the code, but the data is all read-only data, so With a modern OS, it's only loaded once for all the processes or what. Anyway, okay, acknowledgements. Of course, as usual, a Ruby community and mods, and this time especially my student Ida Kohe. And the presentation is also available, and I'll make sure it's linked. Okay, thank you.